So what I'm going to talk to you about is, as the title says, about using machine learning to enhance sensitivity of gravitational wave searches. But in particular, I'm going to be talking about burst searches, okay? For those who are maybe not so familiar with the field, may need to know what burst searches are, and I'll put that in context at the beginning. And then I'll talk about this particular algorithm, coherent waveburst, which is widely used in the collaboration for burst searches. And then I'm going to talk about improving coherent wavebursts with Gaussian mixture modeling. Well, first I'm going to tell you what Gaussian mixture modeling is and how we apply it to it. And I'm going to demonstrate at the end by applying it to the O3A search. So the third observing run was split into two halves, and we just did it for one half just because the data was there and was easier. And then some summary. So as a bonus, I'm just going to be sort of cheeky advertising here, that I can talk about GANs, generative adversarial networks for burst generation if you want as well. But I think there's not going to be any time to talk about that. OK, and firstly, I want to highlight that I'm from Glasgow, as Marco mentioned, and there's a wide range of machine learning activities at Glasgow. And here's my attempt at looking cool with some text speak for that, which is that thing. And you can see that there's work on convolutional neural networks. Joe Bailey, who spoke just before me, was talking about that. And there's also work on conditional variational autoencoders, which also Joe just talked about a little bit briefly as well. And then there's also use of this thing called normalizing flows. I'm not going to talk about it, unfortunately. I'm just going to introduce the term to speed up nested sampling. So nested sampling is a way of sampling the likelihood space. And this is to make it go faster, and we have some work on that. Some people like to consider Gaussian process regression as machine learning. It's a very wide definition, I guess. And this was done by Daniel Williams. And I actually talked about this at IPAM 2 years ago. And more recently, we demonstrated that we can use this generative adversarial networks to generate burst signals, to generalize basically the waveforms, the signal morphologies that we used to characterize our searches. And the thing I'm going to be talking about today is this Gaussian mixture model for gravitational wave burst searches. OK, because this is a talk in the first session of the whole meeting, I just thought that I would just remind everybody of some sort of introductory aspects to gravitational waves. Deep already did some of that in his talk, and I'm very grateful for it because this is, again, a 2 or 3 slide intro into gravitational wave detection. So just to remind everybody, we have a global network of gravitational wave detectors. So here in the US, so this is an interesting view. We are looking from effectively the North Pole here, OK? So that's North America, that's Asia. Unfortunately, Australia is down there somewhere on the other side. But nonetheless, so the LIGO detectors are here. And then Europe's over here with Virgo and the Geon detectors. They'll very soon, in a few years, be LIGO India. And right now, there's also Kagra running. So in the third observing run, we had there was some overlap between Kagra and the LIGO detectors and Virgo and Geo. And then in the next observing run, the fourth observing run, again, this network will be in operation for the fourth observing run. And then in a few years' time, LIGO India will be included in this network. Here's another sort of visualization from our Australian friends, Ozgraph, about the detections that have been made. Okay, so each box is one detection, and here we can see that in the first observing run we have 3 boxes, 3 detections. The second observing run we have 8, I think 2, 4, 6, 8, yeah, 8 detections, and then on the third observing run, which is split into 2 parts, O3A and O3B, we have these 90 observations. Okay, so this is just visually you can see by color coding the sort of jump in volume of detections between the first 2 observing runs and then the third observing run. And this jump in volume comes from the hard work of the instrumentation people to improve the sensitivity and the stability of the detectors so that we can probe much further into the universe. Okay? There's also other information in this. For example, the numbers here are the total mass of the objects and so on and so forth. But I don't really want to get into that. One of the reasons why I'm showing this is that despite us having all these many wonderful binary detections, all the detections we've had so far come from this particular class of compact binary coalescences. Okay? Joe Bailey before me just showed some version of this graphic. On the top row, my axes are a little bit different from his axes. On the top row, we have the transient, the short duration gravitational wave signal types. On the bottom row, the long duration signals. And then on the vertical, you have this modeled, so easy to model signals. For example, the binary model, the binary coalescences, and the continuous waves from rapidly rotating neutron stars. And then the poorly modeled or unmodeled are these burst sources or the stochastic background wave, which is akin to the cosmic microwave background or some astrophysical foreground. And as mentioned before, burst sources can be supernovae, but they can also, burst searches are, if you like, discovery machines, okay? We want to observe signals that are not so well modeled and discover new signals in the universe, gravitational wave signals. And you will see that that actually includes some of these binary signals. So binary black hole signals, in particular, can be observed and detected by burst searches because of the broad parameter range aspect of these particular algorithms. Let me just talk a bit more about what these things are. So sometimes I've referred to as generic transient analyses or generic transient searches. I just call them burst searches. And the philosophy behind these searches is that they're designed so that we don't need any prior knowledge about the phase evolution of this expected signal. The waveform morphology does not need to be very precisely defined, okay? And basically what we're looking for in sort of one sentence is we're looking for correlated excess power in multiple detectors, okay? And because gravitational waves will generate the same signal modulo some properties of the detector, but they will generate the same signal in multiple detectors. And that's what we're looking for, okay? And there are advantages to these burst searches. So for example, because the nature, by this very loose definition, burst searches cover a very broad parameter range, okay? So they can overlap with well-modeled signals, in particular these short transients from binary black holes, and we detect many binary black holes. But also, we can detect things that the model searches cannot detect. Binaries, some binaries we can detect better. For example, there are publications from here and here that say that, and then they demonstrate that basically burst searches are more sensitive than template-based searches for high mass, and when high mass, I mean more than 200 solar masses-ish, okay? So very intermediate mass black hole sort of regime. But also if there's significant orbital eccentricity, so that they're not circular orbits for the binary black holes, but sort of, yeah, eccentric. And also, as I mentioned before, burst searches are meant to be discovery machines. We want to observe sources of gravitational waves that are not so well modeled as you would expect from, for example, from all the binaries that we've been observing. To sketch what a typical burst search will look like, first we will weight the data with basically what's called whitening. Okay, we'll make it so that the data is reweighted by the frequency, the noise of the frequency. Sorry, reweighted by the noise in each frequency band. Okay, and then we make a time frequency representation of this whitened data. So we do a decomposition, for example, a spectrogram. Most people will think about when we talk about time frequency decompositions. But in particular, burst searches like to have wavelet decompositions. Okay. Because we don't know exactly the duration or the frequency content of the signal, wavelet transforms provide us with a multi-scale decomposition of the data so that we can actually be sensitive to things that are either high frequency, low frequency, long and short, up to a certain degree, okay? And so that's why wavelet decompositions are popular in burst searches. And then we want to identify this correlated excess power in multiple detectors, okay? And finally, once we identify this, we need to have some way of estimating the false alarm rate for what we observe. And between these two steps, we can make a declaration of whether we observe something significant or not. And then the last point I have here is just as a sort of aside that we can have all-sky searches, which is what I'm going to be talking about today, searches for gravitational waves of poorly modeled gravitational waves from anywhere in the sky at any time. Okay, this is what we call all-sky searches. Or we can have targeted searches for particular sources, like magnetars, from gamma ray bursts, from this and that, and so on and so forth. Okay. What I'm going to be talking about now are mainly all-sky searches. Okay, so this is a sort of nice graphic to show you what a burst search could do. To sum it up in one line, it's a bit like match filtering. It's a bit like template-based filtering, except the template is taken from one detector to apply to the other one. Okay, that's sort of a quick way to think about it. Let me just replay this video. This video is nicely made from Reed Essig. It's an animation really. And what you have here is a simulated gravitational wave signal here, gravitational wave signal here. Everything else, all the fuzz is the noise, and the bold lines here are the sort of underlying signal. Okay, and so we want to correlate again, and we can see that when you correlate, then at the right time, when these two things are maximally correlated, you get a ding, a boom in your statistic, and you say, aha, there's something there. Okay. So this is what you would do, and you need to shift it by time because you don't know where it came from in the sky, and therefore you don't know the time delay between the arrival time of the signal in one detector versus another. Okay? So there is one small time shift associated with the physics of light travel between multiple detectors. Okay? And then we apply another time shift, and this time shift here is large, so that it's larger than the light travel time across the Earth. And this is to make sure that we are now looking for unphysical correlations in multiple detectors. And these unphysical correlations in multiple detectors allow us to estimate the background. Okay? And so again, between the background and the correlation, we can try and figure out the significance of these signals. Okay, and one more thing I want to mention is that gravitational waves have multiple polarizations. Hopefully we know this by now, but just to remind everybody. So there's the F plus and the F cross polarization. Okay, this is the plus polarization. It sort of oscillates this way. And then this is the cross polarization and oscillates that way. And when you have multiple detectors, then what we like to think compared to our EM band friends in astronomy, that gravitational waves are omnidirectional, they actually have directional sensitivity, right? So here we have, if you like, the strength, the overall strength of each detector's sensitivity to each polarization, and we just sum them and square them just to get a sort of visual view of them. This F plus is the antenna, the directional sensitivity to the plus polarization. F cross is the directional sensitivity to the cross polarization. And then when we do this, we get a map like this for the GEO detector, which is in Europe, and we get a map like this, which is for Livingston. Okay, and we see that GEO is about here, and so directly above and directly below is where it's most sensitive, and then where it's looking down the 45-degree angle between the arms, it's the least sensitive. And similarly for Livingston, it's about there, and so directly above and directly below, it's most sensitive, and then the blue is where it's least sensitive. Okay, and so we have multiple detectors in the network around the globe, and we have multiple detectors around the globe, which is a good thing because it allows us to observe the multiple frequency bands. But we also have multiple detectors in the US, which are deliberately aligned so that the sensitivity, the directional sensitivities are very similar to maximize detection. That's what the LIGO detectors are, or that's how they have been oriented. Okay, so why am I mentioning directional sensitivity now? Well, because I'm just going to sort of formulate very quickly how we would construct a burst search for this correlation kind of thing, okay? And so we can formulate that the data is just the antenna pattern multiplied, the directional sensitivity, F, right? Multiplied by the signal, H, plus some noise, okay? And if we want to write this out in matrix form, because inside here, it's buried inside here is the information about multiple detectors. And so if we have multiple detectors from 1 to capital D number of detectors, then F and H are expanded to look like this, okay? F is the antenna pattern, the directional sensitivity corresponding to each detector. There's only one pair of H because there's always only one signal. The signal came from somewhere in the sky, right? So there's just H plus and H cross, okay? And then there's noise, and the noise corresponds again to each detector. It's independent. It's assumed to be independent for all detectors. So we see that actually from this formalism, right? We actually have the data vector is a single column vector, And the antenna pattern can be considered a two-column vector, right? Where the number of elements in the vector corresponds to the number of detectors, okay? And so you can see that if you have two vectors, one here and one here, then these two vectors form a plane. And so anything that is a signal should lie in the f plus f cross plane, right? Because anything, the signals is always a projection of this vector and this vector here, okay? Plus noise. Anything that does not lie in the f plus f cross plane should not be a signal, okay? And so by this very simple sort of approach, and writing it down this way, which was done very many years ago by these guys, you can actually see that you can formulate a null stream where you construct a new statistic that is the perpendicular to the plane, and that gives you your null stream. So you can construct some operator A, if you like, where A times F, which F is the two-column F plus and F cross, is equal to 0. And it's easier to visualize because in 3 dimensions we can see them better or think about them better. If you have 3 detectors, then this thing is just a 3-element vector, and so the A direction is just a cross product between the F plus and F cross. Okay. So in just this very simple term, you now have a generic way because it makes no assumption about what H is, right? You just need to construct this A, and you can cancel out the signal. Okay, which means you now have some sort of weighted version of the noise, which is why they call it the null stream. There's no signal in it. And that gives us another sort of a handle on the properties of the noise. Okay, so again, it allows us to better estimate the background. Now, as it turns out, after many years of looking at this as well, getting just the null stream to use on its own is insufficient, and you need to construct other statistics associated with your signal and your noise. So this is a slide, a very old slide I stole from friend and colleague Patrick Sutton. I think he knows. Patrick, if you see this recording, it's yours, all right? This is the green plane. This green plane, again, is the F plus and F cross plane. And here you have, the purple thing is the detector, the signal, the data arrow, which consists of the data in the F plus direction and the F cross direction, and then some noise direction that kicks it out of the plane, okay? And so you can construct things like this thing called the hard constraint, where if you only look at one polarization, you get one statistic called the energy in the plus polarization. The null energy is this thing here. And then you can also just have the incoherent energy, which is basically the sum of the correlation between the multiple, or rather, instead of correlating the multiple detectors, you correlate the power in the multiple detectors, which is what this incoherent energy actually is, okay? So these are some kinds of statistics that you can construct from a burst search, and this is more or less what coherent waveburst does, some version of these things. And I mentioned coherent waveburst, so I need to talk about coherent waveburst. So CWB or coherent waveburst, I'm going to use this interchangeably, is one of these searches, and it basically made the first detection of 150914. As I mentioned before, it identifies excess power across multiple detectors. And it does it not just by, if you saw the animation earlier, just by correlating the data. You have to it takes into account things like the directional sensitivity, the time delay, and so on and so forth as well. So it calculates some likelihood that the signal came from somewhere in the sky. And the idea, of course, is that the environmental noise is not likely to be consistent with all these features, and so that's how you cut down on that. Let's see. So we estimate the background by applying the unphysical time shift, as I mentioned before. What I want to say here is that the output from coherent waveburst is this thing we will call a trigger. Okay, a trigger is something that of interest. It's not yet an event. It could be noise. In fact, it almost certainly is noise usually. Okay, and the point is that each trigger is characterized by a large number of attributes. And just for fun, you're not meant to be able to read this. Here's the header for all the different attributes that coherent waveburst spits out. Okay, now some of these attributes you will identify as just being housekeeping attributes, how much time lag was applied and all that kind of stuff. But some of these are actually sort of properties to do with the signals, okay? And buried in all these attributes, it tries to capture the signal. And so what it does then is it takes all these attributes and then it applies some sort of massaging, post-processing, okay, to try and distinguish between the background events and the signal events. And that's how it makes a detection, okay? I think I say this here, okay, right. So yeah, so the standard coherent waveburst procedure is to characterize each trigger by applying bins in particular parameters and applying thresholds in these parameters, okay? And the process is semi-automatic. It's based on experience because this thing has been running for a very long time. And it's also based on humans, looking at scatter plots and trying to optimize, looking at multiple scatter plots, trying to optimize how to threshold these things, okay? And then once you have a set of thresholds, you maybe look at the receiver operative characteristic curves, the ROC curves, as we like to call them, okay? And, this process, as you can see here, it's manual, all right? It's also, the thing that I was thinking about is we need not do cuts, thresholds that are fixed on a particular parameter. And I'll show you one of those examples in a minute. We could be more flexible, and we could do something that is not necessarily a single cut that is optimized manually, okay? And this is basically our motivation for doing this Gaussian mixture model work. And at the end here, I just need to put an aside as well. To characterize the signal space, because we don't have any well-known burst sources, apart from supernovae, we just use ad hoc waveforms. So waveforms that we make up that kind of look like what we expect for bursts, and then we do simulations and injections to try and get the sensitivity, okay? So, well, okay. Yeah, so the motivation for doing this Gaussian mixture model is basically we want to minimize the need for this binning and thresholding. The procedure is, the philosophy is all here, okay? I'm going to talk about it in more detail because the devil is always in the detail. But if you don't care about the detail, you can now turn off for a few slides if you want to and just think about something else. Anyway, the idea is very simple. We construct two Gaussian mixture models, okay? One to model the signal parameter space as defined by the injections, by the simulations. And the other to model the background space as defined by the time-shifted unphysical background, okay? And so now we have this sort of n-dimensional multi-attribute space modeled by multi-dimensional Gaussians, one for the signal and one for the noise. And the very nice thing about Gaussian mixture models is that you can ask what is the likelihood of an event coming from the signal model or the background model, okay? And from the likelihood, you can do a likelihood ratio, which is what we do, and say, what's the probability, what's the likelihood of this versus that? And that's all we do. And that's our new statistic. No bidding, no modeling, no nothing. We just say fit our Gaussians onto the parameter space. Come back, we calculate the likelihood, the log likelihood ratio, and we just apply one threshold on that one statistic at the end. That's the thing, okay? Okay, there's a few more subtle details, but let's talk about that now. It has to be said, right? This is not the only work that sort of does it in this spirit. More recently, the Florida group who wrote coherent waveburst also using this thing called boosted decision tree, XGBoost. And they've been doing it to discriminate binary black hole signals from background. And they've done this with much success as well. And so they have a publication about this, which I put here. And it's very nice, but I'm not going to talk about that today. I'm just going to talk about our approach. OK, so in Gaussian mixture models, basically, the name is, it does what it says on the tin. You have this, if you think of this, any parameter space, like the signal parameter space or the background parameter space, right? You have all these bazillion attributes, and there's this blob that's defined by these triggers in this attribute space. So we want to just try and model this blob by some combination of Gaussians, okay? So this combination of Gaussians is expressed here. Your probability that something, this x, belongs to the model, and the model is defined by a weighted sum of Gaussians. You see, W are the weights, okay? N is a normal distribution, the Gaussians. And each of some mean, mu, and some covariance, sigma, okay? And so mu is the location, and sigma, if you like, is the size of the blob, right, in this n-dimensional space. So x now is basically the attributes for one event, okay? So however many attributes you have, that defines the dimension of x. On the other hand, we don't just have one x, we have lots and lots of x's for all the events that we have in the background and all the events that we have for our simulations, okay? So we have capital X, and now we want to calculate the likelihood. Capital X is just the product of all the little x's, right? This is joint likelihood across all the little x's for where theta here is just shorthand for writing all these other parameters that we don't know, okay? What's phi? Oh dear. Sorry, so at some point I went between calling phi and w the weight. So phi is w, phi is the weights, okay? Apologies. I should not change my nomenclature halfway, especially in the Maths Institute, I'm being busted. Okay, right, so the log likelihood now looks like this. Again, it's just a log of that, it's a log of this thing. But you have this expression here, and if you want to find the maximum likelihood for this expression, we can, well, there's an analytic way of solving it to get that the mean, this is a mean hat now, the estimated mean, the optimal mean for all the Gaussians, for each Gaussian k, right, is basically like the usual Gaussian mean, except there's this R factor, weighting factor here. And the same with the covariance. It looks like the usual Gaussian covariance, except there's this R factor here. And the R factor here is defined by this, which you can see is just basically the weighted Gaussian normalized to all the sum of all the Gaussians, okay? So if you like, the R factor is a normalizing term for all the many number of Gaussians that you have, so that everything ends up being a probability. So in practice, we have to use this thing called expectation maximization, and we iterate across this to get the locations and the sizes of our Gaussians. And so that's how we fit our parameter space. And just a reminder, we create one for the signal parameter space based on the simulations, and one for the background based on the time-shifted, unphysical time-shifted triggers, okay? And so here's a visual sort of representation of GMM. I just took this, by the way, GMM just lives in scikit-learn. And so you can just download it from scikit-learn and play with it directly. It's not really that fancy. We didn't have to write very much of our own code, in fact. So here is a simulation, and this data set is a two-dimensional data set, and they've color-coded the multiple Gaussians, 1, 2, 3, 4, 5, that they use to generate this data set. So if there's no color coding, you assume that this is one data set, and you don't know that there's all these Gaussians here, okay? Then you apply Gaussian mixture modeling, and it says, here are your 5 Gaussians, which is exactly where they should be. Okay, so they predict the Gaussians very well, and they also predict that there are 5 of them. Okay, now the thing I haven't told you is how did it predict that there are 5 as opposed to 6 or 7 or 4 or 3? Okay, and the way it does that is by using this thing called the Basin information criteria, or the BIC. And the BIC is basically an approximation of the base factor. And it's just k times the likelihood, k times the log of the number of parameters minus this penalizing parameter for the, hang on, I get it. So, sorry. This is the likelihood, and then you combine it with the penalty factor for the number of, I always get these two mixed up. Sorry. Yeah, and this is the penalty factor for the number of parameters that you use to fit the model. So you can see that the number of Gaussians is here, okay? And for the example that I showed before, your BIC score is high, and then when it reaches an optimal number at 5, it's the lowest, and then you're overfitting now, so the BIC starts to rise again, okay? And so the BIC is very useful to telling us how many Gaussians to fit. And the way we do it to figure out how many Gaussians to fit at the end actually is a very sort of brute force way. We just cycle through and ask it to GMM to say, GMM, does 10 work? Does 11 work? Does 12 work? And then we just compare the BIC and we find the minimum, okay? So it's relatively straightforward. It's not a very difficult thing. So what did we do? For O3, we looked at these 12 attributes. So we needed to get rid of some of the attributes that were, many of the attributes Firstly, as I said before, many of them are housekeeping. It tells you, for example, what time shift you applied, which is not really a function of the signal. It's just for keeping track of what you did. But there are some parameters, such as the frequency and the duration, that is a function of the signals that you injected. You simulate some signals, and you have some frequency and some duration. The problem with the burst situation is that unlike binary black holes, where you have an astrophysical idea of what the distribution of the parameters are in your binary black hole space, your masses, and for example, you have an isotropic distribution, or so on and so forth. For bursts, they're so poorly defined, we don't know how to distribute these things, okay? So if we throw in the frequency and the duration, then we're biasing ourselves because the injections, the simulations were developed for the all-sky analysis, okay? And they were not sampled uniformly in frequency, which means that if we apply our modeling to that particular parameter, we are biasing ourselves to particular frequencies. And this is only because we are using a set of simulations that were designed for a different purpose. The simulations were designed to characterize the sensitivity of the searches, not to reflect an astrophysical modeling of what we expect, okay? So this is one of the points that I'll come back to at the end, is that sometimes, and probably, if we want to think about astrophysics, we may want to think about how we design our burst simulations to reflect what we think could happen with these kinds of signals. This is actually much more complex than what I just said in one line, and we don't need to discuss this today, but I'll just mention it now. Okay, anyway, these are the parameters that we've chosen. You don't really need to know what these parameters are, but I can say very quickly, rho is basically a function, it's proportional to the signal-to-noise ratio. Net CC is basically an indicator of how well correlated the signals are between multiple detectors, okay? Norm is just some normalized, well, actually, I'm not very sure what norm and penalty are anymore, so I won't say very much about those. And this is this network energy density, which is some sort of another reflection of how strong the signal is in the network, okay? And then you have these Q vetoes, which are a handle of trying to get rid of these very annoying low-frequency glitches, these transient spurious noises, okay? And they apply a threshold on the Q veto to get rid of these things, but we don't apply a hard threshold. We do something else instead. The E core is another way of saying a correlated energy. And then this other L veto is another way of getting a handle on another aspect, which I forget exactly, but it's just another sort of way of cutting away spurious background events. But instead of applying hard thresholds to these parameters, we now throw them all into the Gaussian mixture model. Now, there is a data reduction step, okay? We can't throw everything from, if you like, the zero value to whatever is observed, because there's too much data. And so we do a selection in our cells, and we think that this does not affect our sensitivity. So we select only events that have rho bigger than 5.5, and this is this net CC factor of 0.5, okay? This is much below the usual CWB thresholds. And again, this is mainly as a data reduction factor. Okay, so yeah, there's another thing I just want to mention very quickly. We need to reparameterize the distribution of these attributes because this is a Gaussian mixture model. It fits Gaussians to the parameter space. However, some of these distributions are not very Gaussian, okay? And because it can't fit with these Gaussians very well, it affects the performance. And so we need to reparameterize some of these things, basically by either applying logs or sigmoids functions and that kind of stuff, so that they become more Gaussian. Because some of them mostly lie in a very narrow parameter space, like a delta function, and then there's a small sort of spread elsewhere. And we need to spread out that delta function so that it looks more like a normal distribution, so on and so forth. So that's why we have this reparameterization. And I'll just mention it very quickly. You see, this is how we reparameterize some of these things. So this is basically rho, even though it's called E to C. This is net CC, energy density, E core, norm, and then there's all these other parameters. Anyway, this is our reparameterization. And we see that once we reparameterize this to be more Gaussian, or at least more spread out, then we find that actually, firstly, we see that it does something in the sense that we now need fewer Gaussians to fit the data, okay? So in our signal, We used to have 113, and now they only need 90, and so on and so forth. So that's good and useful, but it's also one of the things that we can come back to and think about later. OK, and we need to train, because this is an iterative process. We need to have some training data and then some testing data. And so we take the background, the time-shifted background for just the Hanford and Livingston detectors, and it gives us about 1,000 years of background, OK, from all the many, many, many time shifts that we have. So if you like, we repeat the experiment many, many times, but without gravitational waves. And now we have effectively 1,000 years of repeated experiment to estimate the background, OK? And so firstly, we need to, the terminology is a bit funny here, but this is chosen by Dixina, who's done most of the work. So firstly, we need to tune the data. So we need to optimize, for example, the big values for fitting the signals and finding how many Gaussians are to fit the data. And then we train. So we ask it to rearrange the number of Gaussians, the fixed number of Gaussians, to how well it can fit this thing. So it changes the location and the sizes of all the Gaussians. And so we use 70% of that background data for training. And we're left with 20% for testing. So if you like, this one is where we test and see the performance of our data. And so even though we had 1,000 years of background, our false alarm probability at the end, the best thing we can estimate is 1 per 200 years, because it's 20% of 1,000 years, OK? So anything more significant, we can only say it's more significant than that, just as something to think about. And I mentioned before that we use these Adhoc waveforms. These Adhoc waveforms are sine Gaussians, Gaussian pulses, white noise bursts. So here we have sine Gaussians, what they look like, ring down. We can do ring downs as well, white noise bursts. We have a Gaussian pulse, and then we can also train it with binary black hole mergers, although we don't. I just had this as part of the images, but these are the things we trained it with, OK? And then for robustness, we show it waveforms from core collapse supernovae, OK? Because core collapse supernovae typically can look like some combination of these things. And we want to know whether we've overtrained the system, because the burst searches have to be very general. We want to still detect things that we didn't train on, right? So we train it on these waveforms, OK? And then we show it these core collapse supernova waveforms that have not been shown in the training to see how well it's performed, OK? If you like, what we call it? Out of sample training, some people call it, I guess. Out of sample testing, maybe. Anyway, OK. So the last thing I want to say is that we have now, for each trigger, the probability that it belongs to one of the models. So we call it W in this nomenclature. And WS is the probability, the log likelihood that it belongs to the signal model. And WG is the probability that it's a glitch or a background model, OK? And so when we have the log likelihoods, to take the log likelihood ratio, well, we don't take the log likelihood ratio. We just subtract one from the other. And so this is our T statistic, which is our detection statistic, OK? And you can see already it's quite promising, because this is a T on the horizontal axis. 0 will correspond to the same log likelihood ratio for each model, OK? And all the background events, or a large portion of the background events, the majority of the background events hang out at negative, right, T. And the simulations, all these other non-blue colored lines, are basically greater than 0, OK? Now, here's the bit that we have to be careful about, that there is overlap. So some of the background events go into this region, and some of the simulations go into this region. So we are not perfect, of course. But OK, we can already see that this is very promising, that there's some separation between these two just by using the T statistic. And lo and behold, if we construct now if we just apply a threshold, oh, I went to this too quickly, but OK, if we apply a threshold that corresponds to a false alarm probability of once per 100 years, if I remember correctly. So at that threshold, no, sorry. Let me restart. I jumped to the wrong part in my brain. So these are the ROC curves, OK? And for the dashed line is the false alarm rate versus detection efficiency for coherent waveburst, standard coherent waveburst, with the standard sort of procedures. And just for those who are unfamiliar with the ROC curves, right? you want it to go to efficiency of 1 as quickly as possible. So basically, you want it to be as far on the top left corner as possible, right? Because it means that for a very, very low false alarm rate, you go bing, you can detect everything, so you don't have to worry about anything. Okay, that's one thing to remember. So we want the curve to sort of be up here somewhere as much as possible. Secondly, is that for gravitational waves and for burst searches, or just all sky searches in general, we are talking about false alarm rates of 1 per 100 years for detection. Okay, so we are looking at here the horizontal axis is in years, and that's 100 years. Okay, and this is the region that we really care about. Actually, is where we can declare, if you like, a new discovery. And we see that for our various traditional ad hoc signals, the solid line, which is the GMM, the Gaussian Mixture Model approach, does much better or as good as, in fact, no, much better than the standard coherent waveburst approach. Okay, don't be fooled. Unfortunately, not all these are on the same scale. This is 0.8 and 1. Here's 0.3 and 1, and this is 0.8 and 1. So while this looks much larger, relatively speaking, is about the same as this. But nonetheless, our Gaussian Mixture Model approach means that we're better at all false alarm rates with coherent wavebursts. Okay. The other thing to note, which is a bit technical, is that here, as we change the false alarm rate, we're actually changing the T threshold for the GMM, because that's our detection statistic. But for coherent wavebursts, they are changing the rho threshold, which is the strength of the signal noise ratio, if you like, here. So we're varying different statistics, but we can plot on the same curve false alarm versus detection efficiency. Okay, but and here's one of the reasons why we could do better. So here, and here's an indication of why we could do better. I have to say we need to do more investigation on this. So the dashed line I have here is the threshold from standard CWB on this parameter CC, or net CC, okay, which is 0.8 for this search. And here's the rho, which is the strength of the signal. And here is basically where the red dots are the standard coherent waveburst detections, and the green dots are the ones that we recover, the injections, the simulated signals that we recover for our GMM. And so we recovered all these signals down here, okay, that were otherwise would be lost if you just did a straight cut. We need to do, this is only for the detection, but you can see from the rock curves here, we don't lose in terms of false alarm rate because our rock curves are higher at each point. Okay, so even though we're detecting more signals, we are still suppressing our noise. Okay, which is why it leads to this. It has to be said as well, the GMM misses some of the signals on this side. Okay, so it's sort of it's not a one-to-one correlation. You can see as we see some, and we miss some, and so on and so forth. Either way. Okay, and then the robustness test, which is where we have the supernova searches, and we can see that the dashed line is for a tuned CWB search. Well, no, it's what CWB does. Sorry, it's not tuned. It's just a CWB search for these particular signals. And so the dashed line here corresponds to the CWB, and the black line corresponds to GMM. And in just almost every case, we are as good as, if not better, than CWB, especially in this 1 per 100 years regime. Okay, so I would claim that we are still as robust and as general as what we have for standard CWB, even though we did not train on these signals. And then as a final sort of sanity check, coherent waveburst, standard coherent waveburst, found these 15 binary black holes. The way they plot these things is a cumulative histogram of the number of events versus the inverse false alarm rate. And so if you see the green line is where the detections mean that our detected binary black holes mean that this curve deviates from basically the null hypothesis. So the null hypothesis would be this inside this region, okay, and this line here. And so all our black holes are observed here, and for the GMM we have exactly the same sort of behavior, almost exactly the same sort of behavior. We observe also the same 15 black holes, okay? So we don't lose anything, again, even though we are more sensitive to all these other kinds of signals on the rock curve. And one of the interesting things is that the green line is for coherent waveburst, which sees two events, and the two events are at this date and they have inverse false alarm rates of maybe 2 per year to 5 per year. But then for the GMM analysis, they actually are completely insignificant, if you like, okay? So this thing should be large if you want it to be significant, and it's not. It's for the GMM, it's completely insignificant. So it's consistent with background. This is the 15 binary black holes that I just mentioned that were observed by both GMM and CWB. This is the table. Please don't look at all the tables. What I want you to look at, all the numbers. What I want you to look at is actually the color coding and to some extent these the last 2 columns. So the last 2 columns are the inverse false alarm rates, which is a reflection of the significance, the detection significance for these events. These events are all binary black hole events, okay? And the interesting thing is that we see, for green, we detect the event that is more significant than standard CWB, okay? Given that we have a sensitivity that is greater, right, we expect that we have suppressed more of the background, so we should be more significant, okay? So for the green events, we are more significant in some cases by many factors, 5 or more, or something like that. The ones that are not colored, by the way, are the ones that are marginal, so I can't tell whether one's more significant than the other. On the other hand, there's orange, which is the ones where we don't do as well as CWB, okay? So here you see that CWB sees this quite clearly, and we say, maybe. And then this one as well. This one's very, and this is not, okay. And there seems to be a magic number, and that magic number is a total mass of 60. So if your binary black hole system has a total mass of 60 and over, then the GMM analysis will actually observe it with greater significance. And this corresponds to lower frequencies, okay? And if you think about it, I mentioned it in passing earlier, at lower frequencies, the coherent wavebursts have many of these glitches. For those who know the speak, they're called blip glitches, right? And that's one of the reasons they have to do this binning and all this sort of fancy stuff. But here, there's no binning. We just fit it with the GMM, and then we get it out. And we seem to be doing a very good job of suppressing these blip glitches. On the other hand, at higher frequencies, where the masses are lower, our significances are not as good. This needs some investigation, but this is kind of one of the interesting things to see. The other thing that's interesting is that this particular event basically has very asymmetric masses. Where are you? 1904, 1, 2, okay, down there. So the masses are not, oh no, these are CWB statistics. So these are very uneven masses, and we see them about the same as CWB, if not slightly better, even though it's relatively low mass. But again, because it's asymmetric masses, it seems to give us, the GMM seems to do a very good job of observing that. Okay, that's me. Here are some thoughts in conclusion. So I would like to say that by applying the GMM, we can actually improve the sensitivities, okay? And we're going to implement this for the O4 all-sky analysis. And I want to just sort of trigger some thoughts here to say that we can use this approach for different signal sources. So if you want supernovae, for example, we can try and train these on supernovae specifically, or magnetars, or anything. And also, you can try it on glitches as well. But the question is, the GMM approach is nice because we have all these probabilities, we understand likelihoods, we understand likelihood ratios. But ultimately, it is a classification problem. And we are in a machine learning meeting, right? And neural networks are perfect for classification. So instead, if you throw out all the sort of probabilistic thinking, why don't we just throw it at a neural network? And because we have labels, we know which ones are the backgrounds, and we know which ones are the signals, we just throw it at a neural network and try and distinguish between the two of them, okay? And so that's one of the things we're trying to do. Another thing that I'm thinking about is that CWB is effectively an encoder. It takes all this raw data, right, and it encodes it into these attributes, okay? Your encoder need not be CWB. You could have some kind of machine learning encoder or any other encoder if you like, right? And we don't know if the CWB encoding of these events is the optimal one. It's the most physically sensible one. That's why these guys have put a lot of effort into training these things. So what if we don't use CWB and we just construct a different encoder to improve the classification scheme? And actually, some people are already doing this. For example, Philip Moravsky and Elena Coco and others have this autoencoders for burst searches, where autoencoders is where you put the data in, and then you get the data out. But in between, it's sort of, on the neural network, in terms of nodes, it sort of looks like a funnel, okay? And it tries to encode the data into some smaller number of dimensions. And then maybe from those smaller number of dimensions, which is more optimal, let's say, you could do a better classification. And that's the idea. And they sort of do something like this in this particular paper. Anyway, that's me. And that's a fun thing to do. PhD students use this excuse all the time. Anyway, thanks.